Praveen, we can start the session.
Hello,
Yeah, we can start the session.
we can start the session. Okay. Very good morning to all of you. I am Praveen Dangar, working in gas turbine power station Uran 672 megawatt, Navi Mumbai. I'm a research scholar in the Department of Electrical Engineer, Dr. Babasaheb Ambedkar Technological University, and also a member of All India Institute Industry Forum. You are welcome on this platform for today's webinar on practical application of VSC HVDC in electrical power system by Mr. Santosh Kaware. Let me introduce today's expert faculty. Mr. Santosh Kaware, working as additional executive engineer in REMC SCADA WAMS State Load Dispatch Center, Maharashtra State Electricity Transmission Company Limited MSCB, Kalwa, Thane, Mumbai. Previously, he worked at 500 kV HVDC and 400 kV Padge substation as operation and maintenance engineer. He did his B Electronics and Power from Government Engineering College, Amravati, and MTech in Power System from Dr. Babasaheb Ambedkar Technological University, Loneri. He has 18 years of field experience, and his area of interest are operation and maintenance, design of HVDC, HVDC light, EHV, FACS, SCADA, WMS, and grid operation. He has delivered many lectures on HVDC and FACS in renowned institutes like IITs, NITs, CPRI, NPTIs, and various government and private engineering colleges. He has given HVDC Padge plant introduction to the thousands of students from various engineering college in India during their industrial visit at HVDC Padge substation. He is acting as an external guide for academic projects, dissertations, thesis for B, MTech, and PhD student. He has presented many papers on HVDC in various national and international conferences. He got first prize with gold medal for his paper on VSC HVDC for offshore wind in national conference at Dr. Babasaheb Ambedkar Technological University, Lonere. Also, his two papers awarded first place with trophy in MSETCL. He has represented MSETCL HVDC model in Harit Kranti 2010 and delivered lecture on HVDC at CPRI Bangalore and PGCIL. HVDC conference on behalf of MSTCL. His paper on offshore wind speed forecasting by a support vector machine and power integration by HVDC light in the International Conference on Power and Energy organized by Nanyang Technological University, Singapore, and having affiliation with IEEE Singapore chapter. I request Mr. Kaware to deliver a lecture on practical application of VSC HVDC in electrical power systems. Thank you.
Thank you so much, Mr. Praveen.
Hello?
Am I audible, Praveen?
Yes, you are audible. Please
okay.
Go.
Just a minute. So, welcome for today's free webinar on practical applications of VSC HVDC in electrical power system. So basically, HVDC is a very vast subject. There are many more developments are going on in HVDC, but especially I have chosen this topic that is we can say it's a very advanced technology. So I will try to cover within this 1 hour almost all areas of this VSC transmission. But this 1 hour is really not sufficient for this VSC transmission, or we can say HVDC. Just a minute. There is an issue with the screen. So we will have a brief historical background of HVDC. So we know that in 1880s, DC was invented by Thomas Alva Edison, and again AC was invented by Nikola Tesla. And there was in that period, there was a war of currents. So later on, Thury systems were developed in between 82 to 1930s. Then mercury vapor rectifiers in 1901. In 1929, mercury arc valves was developed by Dr. Yuno Lam, and the first commercial HVDC that was established in 1945 in Germany, Berlin. But that project never came into operation. Later on in 1954, first commercial HVDC operation started in between Sweden mainland and island of Gotland. Then in 1960s, thyristors were invented, and in Gotland project, the thyristors were used in 1967. In 1972, on the larger scale in Canada, up to 320 megawatt, these thyristors were used. Again, microcomputer-based control equipments for HVDC that was developed in 1979. This continuous evaluation in this technology is going on. The highest DC transmission voltage plus minus 600 kV that was in Brazil in 1984. Again, first DC active filter developed in 1994. Then their concept of HVDC 2000 introduced by ABB in 1995. Later on, first triple C HVDC, that is the Argentina and Brazil interconnection that came in 1998. And the new technology which has changed the world of HVDC system, so that introduced in 1999. So it was used in Gotland VSC project. In 2010, again, ultra high voltage DC was used in China, plus minus 800 kV, 6,400 megawatt. Then plus minus 200 kV, that is the another development in the VSC transmission. That is the MMC based HVDC, that is modular multi-level converter based HVDC, that is used in USA in 2010. In India, made one world record that India has developed ultra high voltage DC with a multi-DC, MTDC, multi-terminal DC. And China in 2019 have developed 12 gigawatt, 3,284 kilometer plus minus 1100 kV ultra high voltage DC. So this was the, we can say, just brief historical background of HVDC. And we know these, how the economic of the DC transmission. Generally, we know that DC is economical, the more when the distance is beyond the critical, that break-even point. But now this case has today changed because of the development in this HVDC technology. So now we can go for any distance, there is no issue. And if you see the main power equation for the DC, that is P power is equal to UDC into IDC. So it doesn't depend on this power angle, or we can say sending, receiving in voltages like that. So it is independent of that. Also, it is independent of distance also. And these are the power electronic devices which are making the magic in power system. So we know that there are the thyristors which are generally we use for the current source converter based technology. So that we use at 50 to 60 hertz frequency. So later on, again, GTO, gate turn off thyristors, again developed, and that is used also for the HVDC projects, which are having frequency, operating frequency less than 500 hertz. And later on, again, IGBTs developed, which we can operate the frequency beyond 1 kilohertz, that is up to 2,000, 3,000 hertz also. And again, IGCTs that are also coming into picture, and many projects are coming with the IGCT technology also. So by evaluation of this, we can say power electronics devices. So there is a major development in the HVDC transmission. So based on these devices, we can define some types of HVDC, like current source converter, that is known as conventional HVDC. And again, some modified version into that, that is a capacitor commutated converters, ultra high voltage DC that reaches to plus minus 1100 kV DC. And VSC based HVDC, these are known as ABB, it's a HVDC light. For Siemens, it is a HVDC plus, and for Alstom, it is a max sign. And another thought that is the how to connect, means can we utilize the benefits of current source converter as well as voltage source converter jointly? And that's the beginning, the era of hybrid HVDC. Suppose my one end is a current source converter and other end will be the voltage source converter. So that again, there is a benefit with this, and already such schemes are developed and already in service. So again, there are so many benefits with the combination of these current source converters and voltage source converters. Then how to select any HVDC for my requirement, specific requirement for my project. So for that, there is an effective short circuit ratio that we have to think for. Suppose it is the effective short circuit ratio is less than 1.5, or we can say suppose 0, then we can go for the VSC technology, voltage source converter based technology. And again, we can go for the more than 3, there is no issue, we can go for the current source converter based technology, or equal to 3, we can go for the CCC HVDC. So there are many more options, but for that effective short circuit, these factors should be calculated before going for selection for the project. So based on these devices, these are some technologies like current source converters, that is LCC, that is again CCC, capacitor commutated converters. This is the just improved version of this, where capacitor are placed in series between the thyristor walls and the converter transformers. And this VSC HVDC is exactly, we can say here in the current LCC, we use series reactor in the DC side, that is smoothing reactor. Whereas in DC side, for the voltage source converter based technology, we use capacitors. And again, the biggest advantage of VSC converters, that is we don't require any converter transformer. If you see the LCC HVDCs, actually there is a major cost of conversion equipment plus these converter transformers. And when we go for the VSC HVDC, so not just conventional transformers we can use. So there is a greater saving in this by choosing the VSC HVDC. So these are some of the features of these 3 types of HVDCs. That is power control, then based on their short circuit ratio, which technology should be preferred. Especially if you talk about the HVDC light or VSC HVDC, it is the biggest advantage is there is independently we can control active and reactive power. So that is the biggest advantage. So which is not possible in conventional HVDC. In conventional HVDC, when you vary the active power, you have to proportionally near about 50 to 60%, the reactive power needs to be supplied to this station. Otherwise, we can't transmit the power. But that limitation overcome by the voltage source converter based technology. And it has a black start capability, which is not possible in conventional HVDC. Because in any condition, your thyristor walls must require AC supply. But for the voltage source converter, if one end is charged, you can charge the other ends. So that is the, again, biggest advantage of this technology. It is a compact modular, so there's area requirement is very less. And short circuit, that is contribution. So here this current source converter based HVDC, it is not contributing to the fault current, but this HVDC VSC contributing to the short circuit current to the AC bus to which it is connected. But nowadays this limitation is also overcome with the development of the HVDC breakers that in the last we will discuss about it. So this is a current source converter technology, and this is a voltage source converter technology. So here we can say, if you see, this is the indoor area. Generally, for the current source converter, there are walls are indoor and other equipments are outdoor. Also, we can go for the GIS also for AC or DC side in conventional HVDC also. And if you see the VSC HVDC, so there is a this is the internal equipments that is here, and outer that is external, there is a transformer. So this is a structure of this CSC and VSC. And the biggest advantage of VSC that it is a 4-quadrant operation is possible with the VSC HVDC, whereas it is not possible with the conventional HVDC. If 4-quadrant operation means you are actually playing with the power system parameters. You can adjust the active and reactive power as you required, as per the requirement of your power system. Here, many options we have. Here, if I want to increase the active power, 50 to 60% reactive power, I need to supply. But here, I can, if I want, suppose 2000 megawatt power, but in that case, I can keep reactive power as 0 also. I can keep as minus or plus also. That is absorption or we can say supply of the reactive power. Any option you can play with the VSC HVDC. This is the biggest advantage of the VSC HVDC. And you can control, means you can independently control active and reactive power, which is not possible with the current source converter based HVDC. So conventional HVDC has certain or advantages, but at some disadvantages also. But all these disadvantages are already overcome by the new technological developments, that is a VSC HVDC or a combination of these current source converters and these voltage source converters. So here there are many more advantages, but I will not go through it. You know these basic terminologies. So I will mostly talk about the VSC converters. So there are many more advantages of this technology, that by using the voltage source converter technology, we can go for the formation of the grid, that is a DC grid formation we can do, and it is now implemented also. So there are many more advantages. Just a minute. Just a minute. So these are some of the benefits of the HVDCs. So that is especially VSC HVDC. There is no commutation failure. Generally, in the conventional HVDC, there is a many more problem issues or faults. That is a commutation failure. Means failure of AC voltage result into there is a failure of, or we can say tripping of the conventional HVDC. But here it is this voltage source converters are itself voltage supporting technology. So there is no issue of this we can say especially commutation failure. Again, there is a independent control of active reactive power, fast response, black start capability. So these are some of the benefits. Filter requirement is very low for the VSC HVDC. That's also one of the advantage. So these are some of there is no need of converter transformer. That is also advantage of the HVDC. VSC HVDC. These are the some of the configurations possible. That is, this is a, we can say it is a monopolar operation. It is a bipolar operation like that, like a conventional HVDC. So these are the, this is the basic principle, how these voltages are produced. So output of this VSC, how it will control the parameters of the AC system. So that is all is shown here, how by using the pulse width modulation, there are different types of techniques of pulse width modulation. So by which you can produce the desired output from the voltage source converter. Now there is an era of these multi-level converters, because we know that there is a limitation with the IGBTs, that is a rating is less as compared to the thyristors. So by using the multi-level converters, we can overcome these limitations, and we can enhance the power, especially power handling capacity of the these VSC HVDCs. So that is the MMC HVDC. You will get very smooth output by using the MMC HVDC. So like this. So this is a general typical structure of the voltage source converter technology. AC system 1 and AC system 2 is connected through the VSC HVDC, voltage source converter based HVDC. And there is an overhead transmission line used, but we can go for the cables, and specifically this for the voltage source converter based HVDC, where DC breakers are not used. There we have to generally go for the cables, HVDC cables, because there is a, if cables are used, there is a less possibility of the that is a fault, line fault, especially if it is overhead line, probability of fault will increase. But if it is underground cable, so that's why where there is a no HVDC breaker is used, so cables are specially preferred for the transmission. So by using varying the VSC volt output, we can control the active and reactive power. Here, if you see the phasor diagram, so P is actually can be controlled by the phase angle between VSC and VAC. So by using that, you can control the active power on the VSC link, and reactive power you can control by the magnitude of the output of the voltage source converter. So in this way, you can adjust the active and reactive power. Also, by adjusting the magnitude of the voltages produced by these converters, you can that end can absorb or supply the reactive power. So again, by adjusting the angle itself, that you can control the active power. Now there were some limitations before that, but now ABB has claimed that they have developed it. That is it voltage reaches to plus minus 640 kV and 3000 megawatt. Previous means we can say up to before inventing the DC breakers. So the rating of this technology was very less. That's why that technology term they have used HVDC light, or we can say low power applications. But now you can go for higher power applications also. And especially we go for the VSC with the especially cables transmission. Then there are two types of cables we use when there is a underground or submarine cables. So such cables used for the transmission of the VSC. So these are the development, especially modules development of the HVDC. If you see the latest development, that is 640 kilovolt DC, 3552 megawatt. So that is the highest we can say. We can, with the MMC HVDC modular multi-level converter, we can go for this. And for different rate, that is different voltages and different power handling capacities, we can go for other technologies also. Especially HVDC light with overhead lines. Instead of cables, you can go for the overhead lines. So that is you can 700 to 800 kV and 4 gigawatts of power you can transmit with these overhead lines. With extruded cables and other options are also there. So this is we can say development of the especially walls for the HVDC. So like CSC HVDC, VSC HVDC, and especially now we are going for now this MMC HVDC we are already using. Again, we are going for the IGCTs. And these are some of the practical applications of VSC HVDC we are actually using. Like this VSC HVDC has tremendous applications like connecting remote generation. Any hydro that a remote generation you can connect with the grid by using this VSC HVDC. Interconnecting grids, you can connect two different grid networks with the stable operation with the VSC HVDC. Offshore wind connection. So we know that nowadays people are producing power with the offshore windmills. So their offshore windmills power will feed to the rectifier in the sea area itself. That AC is converted into DC. That DC will again come to the shore, and again there is an inverter station that will convert again DC into AC and will feed to the grid. So that's it. That is the offshore wind connection by using the VSC HVDC. Then DC links in AC grid, that is also we are using. We know that there are gas platform, oil platforms are there, and there is an issue of how to supply power to their that is motors, compressors, they are used on the platform. But nowadays, these technology, especially VSC HVDC, people are using to supply power to these platforms, oil and gas platforms. Now, city center in-feed applications of VSC HVDC. Now in India, if you see the Adani's this HVDC from this, we can say that is MSETCL Kudus to that is RA is an example of we can say city center in-feed, because Mumbai is a metropolitan city, and the first time in India we are supplying this bulk power to any metropolitan city. So we'll discuss on that also. Then connecting remote loads, any remote loads, even we can say that this is VSC HVDC you can use for the this distribution side also. Suppose you have some DC load requirement where you want where it's a we can say especially there is less generation or no generation available in that area, so you can supply this power to that load also, and you can upgrade the conventional HVDC or your EHV systems with the VSC HVDC system. So there are many more applications. Later on we'll see advanced applications also. That is a multi-terminal HVDCs systems and DC grid formation. There are many more benefits by connecting multi-terminal DC link. Redundancy is high into that, reliability is more, and DC grid formation means completely we are going towards stable operation of the power system by using this magical technology. So there are many more connections possible with this VSC HVDC, that is these offshore systems we can connect. Then back-to-back is also possible with this VSC HVDC. Point-to-point transmission is also possible. Submarine plus this underground transmission is also possible with this VSC HVDC. And we will have a brief overlook of HVDC projects in India. Generally, almost all our projects in India are thyristor based. So that is conventional HVDC we are using. But in 2021, the first VSC HVDC in commission in India. So that is Pugalur Thrissur VSC HVDC. So that already taken into service on 19 February 2021. And other conventional HVDCs are like back-to-back HVDC terminal stations, which are connecting our, especially our inter-regional grids, plus for point-to-point transmission, for bulk power transmission. And again, the ultra high voltage DC, so that also used in India, that is Northeast Agra and Champakuru Kshetra and Raigal Puglur and this Puglur Trishur. These are the actually combination of current source converter and voltage source converters. But these are actually, we can say, two different systems are connected to same bus, AC bus. So this is the mixed converters, we can say. This is not a hybrid converter, but it is a mixed converter that we have in India. First time we have used it. So the pole one is commission of this plus minus 800 kV. But these are the thyristor based, this is thyristor based technology. This come into service in 2020. So this is the, we can say, a Raigar Puglur Trishur HVDC system. Then it is actually transmitting 6,000 megawatt from Raigar to Puglur. So that is the, we can say it's ultra high voltage DC, and near about there and another technology. So that is plus minus 320 kV. So this is a VSC HVDC. So both technologies are used in this project. So 4,000 megawatt, generally this is a Tamil Nadu share, that is 4,000 megawatt, and Kerala share is 2,000 megawatt. And distance, if you see from Raigarh to Puglur, it is 1850 kilometer, and from Puglur to Trishur, it is a 167 kilometer. But in between that, it is a mixed transmission. So that is, we can say, some at certain distance, there is a overhead line, and at certain distance, there are DC cables are used. So this is the topology of this, especially Raigarh Puglur North Trishur HVDC system, that is 6,000 megawatt. We know that at Raigarh site, there is a, there are many more IPPs are coming, and power is bulk. In the bulk extent, power is available. So that 6,000 megawatt power we are transmitting through this conventional, or we can say it's a ultra high voltage DC, that is plus minus 800 kV, and that is coming to the Puglur on the Puglur AC bus, and from that Puglur, so there is a, again this VSC HVDCs are used. So this is current source converter technology, and this is voltage source converter technology connected on the same bus. So this is a just, we can say, interconnection of this. So such type of system was proposed by Reliance also previously, from this Padghe 400 kV to RA they have proposed, but because of certain issues that not came into service. But actually, this is the just example of how there is a behavior of the converters. When you current any current source converter and voltage source converter to the same bus, how will be the behavior of the converters? So that is the actually, we can say it's a different studies for the engineers. So this is a 2 gigawatt Puglur Trishur HVDC. Especially this is the first HVDC based on VSC, voltage source converter, in India. So it is a plus minus 320 kV, 200 kilometer distance. So here from Puglur, it is actually coming to Trishur, Kerala. So here overhead line is used, 130 kilometer overhead line. And later on there is a underground cables are used, then feeding to the here AC grid. So this is the VSC based HVDC. Now these are some of the highlights of the upcoming Mumbai Kudus VSC HVDC projects in India. We can say that this is the first India's first metropolitan city center in-feed VSC, that is IGBT based technology it is. If you see the distance from Kudus to this RA, it is near about 80 kilometer. So shortest distance they are following. So cable length will be 80 kilometer. And the power rating of this link is 1000 megawatt. And it has a voltage rating of plus minus 320 kV. So the advantage with this technology for Mumbai and especially for Maharashtra, if you see, so suppose it has a black start capability. Suppose there is a failure of any side, whether it is from Mumbai side or this we can say Kudus side. So one end, if one end is charged, you can charge the other end. So that is the again benefit of this technology. And there is a stable operation, means this Mumbai, especially Mumbai grid will be very stable if this project come into service. So if we go for such advanced technologies, definitely it will going to benefit to our national grid also. So these are some of the field experiences, how there is we can say HVDC system, especially VSC HVDC, playing important role in different types of projects, and how it is saving the system and giving the benefits. So this is a Capri Link project where this VSC HVDC, that they have operated in the extremely weak AC system. Suppose any area, if there is a weak system, there is no generation available, more generation. So in that case also, this HVDC light or VSC HVDC will give you a very stable operation in that region also. So this is we can say, especially it is a weak grid, weak AC system example application of this VSC HVDC. Then stationary load flow optimization between Sweden and Finland, POD control of small signal stability. So again, we will get the damping this stability against the dampings. So that is also in this PhenoScan project. And again, Pacific Intertie, there again, they have used this HVDC to ability to damping, means oscillation damping. And that is a parallel connection of AC ties with the HVDC link. Means they have used this technology in parallel with the existing AC system. So again, by using these especially run-up functions and other controllers, very stable operation can be possible. Now we'll see how is the fault detection and clearing time when there is a fault on the DC. Generally, if you see the AC system 400 kV or 400 kV, 765 kV, so there is a near about 100 millisecond time. So that is given generally 70 to 80 millisecond fault should get cleared. So what about HVDCs? Within how much time this fault should get cleared? So we can say that HVDC has tremendous benefit in fault clearance, because in AC system we use circuit breakers, and circuit breakers are, we can say, these are there are electrical contacts, we can say mechanical contacts are there. So it takes certain time to open. But in HVDC systems, we are using these especially semiconductor devices. So this you can even less than 5 milliseconds, you can open the switches. But we know that the capacitor banks and many more these reactive power absorbing or energy storage elements are used in HVDC. So because of that, there is a we can say certain time needed to minimize or eliminate that especially stored charge into the AC system. That's why that time required, but these switches open less than 5 milliseconds. So that is again benefit of this VSC HVDC. This is the sequence of this, for within how much time these fault currents are cleared. So if you see here, the action started for the conventional HVDC 3 to 5 millisecond itself. And further, there is a sequence of operation into this. And within this 180 millisecond, we can say that line fault gets completely cleared. Line may be energized again because there is a time required to discharge this stored energy into the AC system. And here, if you see, especially these hybrid HVDCs or especially VSC HVDCs, so 5 millisecond, so that it should be less than 5 millisecond. But there is an issue with the VSC HVDC, which are having cables and there is no DC side breakers. So so there is a dependency for the fault clearance on the AC side breakers because of the freewheeling diodes, anti-parallel diodes in the IGBTs, some fault current remain fed into the system, and when the AC side breaker open, then that fault will get cleared. But whenever there is a DC breaker is used for the VSC HVDC, so that fault can be cleared within very less time. So these are some of the time scales given, how these within how much time this fault should get cleared with the different types of equipments. So these are some of the terminal VSCH, different possible combinations of the terminals. How these by using PWM technique, how perfect AC we can, that is output we can achieve. And these are different topologies. Then some of the, especially this portion I have included for the academic people, and this especially how to control this VSC HVDC system. So there are certain basic equations for active reactive power, and these are the control strategies were used. Here phase lock loop, then RPC reactive power control or active power control, then active active voltage control. So these are some of the control strategies used. Again, vector control. This is the one of the method where this DQ type of vector control strategy is used. So these are again how these control systems how they are connected with each other. Like if you see outer control layer means outer system, then intermediate control layer, decoupled control scheme, and inner control layer, control of the inverters. So this will be maybe useful for the academic purpose. This is also control and protection, how that is coordinated for the VSC HVDC. So we'll not go thoroughly through this. These are some of the protections which are essential for the VSC HVDC. Like AC side, these are the conventional transformers. So conventional, we can say protections are used for this AC side. Then converter bus differential protection, converter bus under over voltage, AC filter capacitor imbalance. So many more filter protections are given here. Again, VSC wall protections like wall current differential protection, wall short circuit protection, wall cooler protection. That is we can say cooling system protection based on cooling system. DC line fault, DC cable fault indication. So all these things are included in the protection. How these protections can be coordinated with each other. So that is also mentioned here. And how to test this VSC HVDC simulation setup, how to do it. Fiber optic, how it is used for this we can say wall-based controllers. And this is a 1000 megawatt plus minus 320 kV HVDC flexible type of VSC converter. And now we'll see some of the advanced application of the multi-terminal DC and DC grid formation. Now people are going for the DC grid formation instead of AC grid. means AC grid plus DC grid. We can say jointly also we can do that, and multi-terminal HVDCs. So this already they have implemented, but in this implementation there was an issue of a interruption of the DC current, because we can say up to 2020 just research was going that we can research was going that we can break the DC, and in 2020 that tested and already are now implemented also DC breaker. So how it is, so that DC breaker, by using the DC breakers we can form the DC grid. So this breaker, first HVDC breaker tested successfully tested. It is third-party test on ABB Power Grids hybrid high voltage DC at KEMA laboratory, Netherlands. They have tested, and now that is used also in one of the project. So how these DC hybrid DC breakers actually operate? Just we will have a brief overlook of it. If you see our conventional HVDC, there are generally we can say that conventional breakers are used, but MRTB, that is metallic return transfer breaker, so that is used for the change of mode of power, mode of HVDC. When we have to shift from the ground return to metallic return like that, so then that MRTB comes into picture. But here but that is not isolating the fault. Actually, isolation happens with the by pausing the firing pulses of the thyristor valves. But here in DC HVDC, especially VSC HVDC, we have to actually use especially here we have to interrupt the DC. That is the issue, and that already by using this semiconductor technology, especially IGBT walls or IGBT modules are used here. IGBT modules. So normally this here power is fed through this bypass circuit, and main breaker is actually in open condition. But whenever suppose there is a fault in the grid or VSC system, so this line commutation switch open, and when it opens, it will disconnect this ultra fast disconnector, and in this way that fault current is we can say fault isolated from the DC side. And in that case, the stored energy, these main breakers again connect here. Modules are there, IGBT modules, so that will operate, and we can say this stored energy is absorbed into the these non-linear registers. So in this way, this we can say, especially this DC current or fault current is interrupted by using the hybrid DC breaker. And because of this invention, now there is a practically in many countries, people are going for the HVDC grids or multi-terminal HVDCs. So like VSC, CSC, current source converter, voltage source converter, these all technologies we can connect with this, especially hybrid breakers. So in hybrid HVDC, one terminal is a line commutated converter, and other terminal is a voltage source converter. So here we can say, here the in between Norway and Denmark, there is a hybrid HVDC they have used. One is voltage source converter, other is current source converter. So just they have connect these two countries with this LCC 500 megawatt and VSC HVDC. And here they have used, we can say, cables, some underground and submarine cables they have used. It's a 500 kV plus minus 500 kV, it is plus minus 350 kV. So because of, especially we can say that this DC breakers, now it is possible. Again, many more such projects are coming. These are also Yunnan and other These are some of the projects, 8,000 megawatt. Here LCC and LCC technology, VSC, LCC combination. One end is a LCC, other two ends are VSC. So like that, these are the some of the combinations are used. And this is the first international, we can say, especially in China, they have developed the DC grid. They have connected these four VSC HVDC system with the this especially VSC HVDC. And now we can say that this is the first multi-terminal or a first DC grid in the world where VSC HVDC systems are used to connect this system. So that project also came in service. So these are some of the ratings and diagram of this. So here plus minus 500 kV DC voltage is used. Then it is 170 kilometer length cables. Then 1500 megawatt is the rating of the voltage source converter, this end. Other end is 3000 megawatt. Other is 1500 and 3000 megawatt. So this first DC grid they have formed. These are the some of the projects of HVDC, VSC HVDC in across the world by ABB, GE, Siemens. And we can say that now we can already, we were thinking of to connect all the world in the one grid, and now it is possible because we know that every country is having their own frequencies, voltages different, but by using VSC HVDC or conventional HVDC, now it is possible to connect whole world into one super grid. And this is possible with the combination of AC HVDC system. Now we can say that in 1880s, people thought for the war of currents. Now we can say that now we can say that it is a union of currents. Instead of war of currents, we can go in harmony with the AC and DC currents. And definitely this super grid formation will be come true very soon, because many more countries already started interconnection, like Argentina, Brazil, now Norway, that we have already seen. Like many countries have started the interconnection. Also, we have planned interconnection. India has planned interconnection with Sri Lanka with another HVDC system. In Bangladesh, already we have connected with the Bangladesh through back-to-back HVDC. So these are the interconnections already happening into the world, and there will be the definitely we can say that one world, one super grid. So this is these are the some of the references I used for this presentation. Actually, HVDC is a very vast topic and it requires much more time to cover, because there are current source converter technology, voltage source converter, then hybrid technology. There are many technologies are there. So if you are interested in further learning of this, then this is the platform where you can learn more about the anything, any technical topic here. So now we will have a question answer session. So I'm unmuting to all the participants, and we will have a question answer session. Just a minute. So now unmute option is kept. So you can ask your query, or you can write your query in the chat box. So we will have a good discussion on this technology. So thank you so much for all of you. And thanks to organizer, that is Technovision Academy and All India Institute Industry Forum, for arranging such thing for us. So
Santosh sir, good morning.
Yeah. Yes, sir.
सर राहत बोलतोय
हा बोल
ते
येस सर.
अर्थिंग इलेक्ट्रोडला आपण why we keep at such a long distance, number one,
Yes,
and whether it is overhead or cable, and what is the effect on the soil, because what I have read and I heard from you also, it is normally kilometers away from the main station.
yes,
And what is the connection between the electrodes at two terminal, like feeding end and the receiving end, how they
yes, sir.
behave?
Yes, sir. Okay, sir. See, especially these earth electro stations are
Yeah.
actually for the conventional HVDC. These HVDC, these electro stations are used. Why electro stations are away from the main terminal station? The reason is
Yes, sir.
DC. We know that DC has a electro osmosis property. Whenever you use DC, so there will start the corrosion. So where
Okay.
corrosion of the material. If you ground this electro station very near to your terminal station, what will happen? That current will pass to your terminal station earthing grid, and that earthing grid will corrode and erode, and ultimately after certain years that itself will vanish. So there will be no proper grounding to our terminal station equipments. So for that, we have to go for the distance, generally more than 20 kilometers from this main station, main terminal station. But that distance may depends on the again soil resistivity. How is the soil resistivity of that area? Then if there is a continuous water arrangement is there, so that will be the added advantage to this area, because suppose there is a, we can say, any river, any channel what is there, sea is there, so that will be the best places for the electro station, because we know that if there is a continuous watering, there will be the again it will help to reduce the resistance of that system.
Okay.
So that's why we choose the distance to avoid the erosion and corrosion of the earthing system. We choose such a distance that may vary also. In certain projects, it may away from the terminal station near about 180 kilometers like that also, because we have to maintain that system. Again, there should not be any gas pipeline, oil pipeline in the vicinity of that. So this we actually in HVDC Chandrapur Padge project, especially when we go for the ground return mode, in that case, there was an issue with the gas pipelines of this BPCL, then gas like that, because if we do not do the proper survey and just we put some railway tracks or any these underground other structures, so that will erode or corrode also. Because so that care we have to take while going for the gas pipeline, oil pipeline like that. And even these electrode, especially any substation also. There should not be any other substation in the vicinity. Otherwise, what happened? Their substation will also get the corrosion and erosion effect. And now the electro station, which are at the rectifier and inverter side, how they behave. So actually, by using actually our earth is we can say it's like a conductor having infinite cross-sectional area. And if we go towards the core of the earth, the resistance of the earth itself decreases. When you put a DC current, there are electrodes buried 3 to 3.5 meters deeper. Electrodes are there. When you pass the DC current into that area, so that will go into the deeper side of the earth, because it will follow the least impedance path. So it will not come onto the surface until it is not getting the least impedance from the path from the other structures. So practically, actually, this DC current flows through the ground in case of HVDC. And when it is a ground return mode, it enters into the electrostation of the inverter station, and it actually passes through the distance and it reaches to the other end at the rectifier station. And in this way, path of that circuit completed. Yes.
Yeah.
Any more questions, sir?
That means marine cable is always better, no? Like you are near the sea, so this problem will not be there.
Yeah, if it is that near to see this electrostation, that will be again very good.
Always wet. So
yeah,
resistance
always
will
wet.
be low.
Yeah.
Thank you very much.
Thank you, sir. Other participants also can ask the queries. So any other queries so you can ask or we can otherwise close the session. So if you
Sir, हा presentation आपल्याला reference साठी मिळेल का?
Yes sir, मी शेअर करतो आपल्या ग्रुपमध्ये.
ओके. ते कारण मी थोडा 10 मिनिटाचा मिस केलं सुरुवातीला.
व्हिडिओ पण शेअर करतो.
ओके सर. Okay sir, thank you.
Yes. And thanks to all of you for coming for this session, and especially thanks to the organizer for this making this platform available for such sessions. So we are welcoming all of you to join Institute Industry Forum. So we are having regular these sessions by industry and institution experts. And also there are many, I'm thankful to this platform to arranging some practical these courses. So that is also one of the added benefit for the academic and industry people. So all are welcome once again in this platform. So if